Assalamualaikum and good day to you doctors. My name is Nur Sarah Zalia. Our group has chosen to design a hip implant. So the group members will consist of Miranda Khairun Nisa, Muhammad Aiman bin Muhammad Roslan, Nur Sarah Zalia, me, and lastly Nurul Eza Hazira binti Samsul. So in this video we'll be talking about the introduction, what is a hip implant, design of the implant and the materials selection, the fabrication of the device, material characterization and tools used, and last but not least the conclusion and references. So the introduction, let's begin. So what is a hip implant? As you can see in the diagram here, it's actually an injured hip joint. So what a hip implant will do, it will basically just replace the hip implant so that it could restore mobility and relieves pain for the patient. It will not only relieves pain, but it could also ease the patient's daily routine. So why an individual might need a hip implant is a common reason will be arthritis, or the common reason for elderly people will be fractures in the thigh bone. Last but not least is hip joint tumor. So generally in the biomedical engineering field, there are 4 types of total hip replacement devices, and the common materials used are firstly methyl on polyethylene. The names are simple, it's in the name. Methyl on polyethylene means the ball of the hip implant is made out of metal and the socket is made out of polyethylene, or it has a plastic lining. Secondly is ceramic on polyethylene, which means that the ball is made out of ceramic and the socket is made out of plastic or has a plastic lining. Third is ceramic on ceramic, which means the ball and the socket is ceramic, or the socket has a ceramic lining. And lastly is ceramic on metal, which indicates the ball is made out of ceramic and the socket has a metal lining. So what are the important questions that we need to ask ourselves before getting ourselves a hip implant? So first of all will be, has the surgeon ever used this implant before? It is important to know the surgeon's capability and to know whether the surgeon is familiar with this device to ease and smooth the surgery later when applying the hip implant. Secondly is, how long will it last in the body? We wouldn't want an implant that requires the patient to keep returning back to the hospitals and change their implants. We want something that will last. Third is, will the hip implant help in performing normal activities or rather restrict? The main reason why someone would get a hip implant is to ease their daily routine and not burden it. And last but not least is the material safe. The material has to be biocompatible to the body, because we do not want a material that reacts to the body and causes inflammation or any allergies. I will pass this to my friend Miranda.
My name is Miranda Khairanisa, KIB 190709, and for my part, I'm going to talk about the design of the implant and the materials we chose. So, this is a picture of a healthy hip joint. We have the femoral head, the pelvic bone with the acetabulum socket, and the femur thigh bone. So we focus more on this part to make the implant. But as Sarah said, we need to consider the strength, the weight of the implant, the biocompatibility, and how long will the implant last in the joint itself. Now, the design that we chose will have an acetabular cup. This will be the new ball and socket joint that goes inside the pelvic bone, a liner that will allow head to guide smoothly and naturally, a liner that lines the acetabular cup, and the femoral head that will act as the ball that will fit into the new socket and attach to the stem, and also the femoral stem, which supports the hip joint and provides stability. The femoral stem will be inserted into the thigh bone, which is the femur. For the material selection, after further consideration on the 4 common materials that can be used, we chose the CoP, which is the ceramic head-on polymer lining, for its advantages over all the other materials. For instance, the metal is not biocompatible with the body, and it may be toxic if exposed to the bloodstream and allowed to travel throughout the body. And for ceramic, if we choose ceramic CoC, ceramic head and ceramic liner, ceramic is a brittle material and it has a higher chance of fracture, especially during the insertion surgery. It may fail before being inserted itself. Now, the polymer that we chose is called ultra-high molecular weight polymer, made up of more than 200,000 monomers, making its molecular weight very heavy and thus being very tough. These are the properties of the UHMWPE. These properties cause the materials to have excellent wear resistance, low friction, and high impact strength. The ceramic that we chose is made up of 25% zirconia, 75% alumina, and less than 1% of chromium oxide and strontium oxide to counterbalance the hardness caused zirconia. These are the properties of the zirconia toughened alumina, and this mixture will provide an increased strength and toughness, increased resistance to cracking, chemical and hydrothermal stability. Now, despite the advantages, like all other materials, they are still prone to breaking and degradation. The primary mechanism of wear of polymer is adhesive or abrasive, which can be due to the material itself or its manufacturing process or the sterilization procedure. We can minimize this wear rate by making the ceramic head should be very hard and has a low contact angle of maybe less than 70 degrees, and furthermore, the head should be as smooth as possible and inert oxidation. But if it does happen, the wear particles will be produced, absorbed into the bloodstream, filtered through the kidneys and passed out through the urine, and when you find the wear particles in your urine, that's when you know that you need to have revision surgery. For the ceramic itself, the primary cause of ceramic, like I said before, is that it's brittle and it may fracture, especially if it is exposed to too much stress. If once it breaks, you really need to get a revision surgery to renew the implant and reinsert another new implants, or else it might cause problems in your daily act. That's it for my part. Thank you.
Thank you, Miranda. My name is Muhammad Aiman bin Muhammad Ruslan, matrix number 17166-156. Now I will proceed with the methods of fabrication and the first part of material characterization. Now, for the methods of fabrication for total hip replacement devices, there are 4 common methods. The first method is rapid prototyping, or RP. As the name suggests, it is for a quick fabrication via machine milling using software such as CAD/CAM, Mimix, and SurgiCAD. This method makes geometrically complex, conceptual, and functional solid models. This method is considered an additive manufacturing. For the second method, it is the computer numerical control, or CNC. It is machine milling with precision but with limitations in terms of speed and accuracy, where they both outweigh each other. Automated control of machining tools by means of computer. This method is popular for mass productions that disregard precision in industries. This method is a subtractive manufacturing. For the third method, it is the hybrid technique with CNC. It is a combination of additive deposition and machine milling, which are only used for replicating dimensions on certain parts. This is a combination of additive and subtractive manufacturing. Now, for the last method, which is high precision machining. This method is only for materials that cannot be easily shaped by conventional grinding. It is conducted via a computer software and is a method of subtractive manufacturing. Now, among the 4 methods, we choose the high precision machining for our specific material selection, which is zirconia alumina for the femoral head. Now, oxidized zirconium is an excellent material due to its strength, durability, and nature of being chemically inert. However, it cannot be easily shaped by conventional grinding. The precision machining is to apply precision single point turning to the manufacture of zirconium femoral heads, so it can operate similarly to an actual ball and socket joint. So it operates very smooth. This method is preferred above the other methods, which are RP, which is suitable for making mechanically functioning prototypes, but not for practical use. Meanwhile, CNC milling is limited for its speed, accuracy, and strength, as they cannot produce as smooth and accurate surfaces for the zirconia alumina head as the high precision machining. As the diagram shows there on the upper right, it shows if the femoral head is not as smooth as it can be, which can cause excess friction and cause pain to the user, and it increases the wear and tear. Now, there are 2 steps for this method, whereby the first step, the cutting tool produces contours or the rough shape that falls short of the required specifications. After that, it uses an inspection feedback system to calculate a path so that the tool will then proceed to smoothen the head of the zirconia on the workpiece, as you can see in the diagram. However, before finalizing the product, we need to fully understand the properties of the materials used in all aspects. Therefore, we must utilize tools to study its properties and microscopic structure to ensure its suitability. Now, the properties that we want to analyze are the thermal properties using TMA, surface properties using SEM, and the mechanical properties using the flexural, compression, and tensile tests. Now, I will briefly explain for the thermomechanical analysis, which utilizes a dilatometer. Now, the said meter has interchangeable probes which can simulate varied loads between 0 to 100 grams. Now, this enables us to analyze the change of dimension of a material at different different temperatures. This method is capable of testing polymers and plastics, metals, glasses and ceramics. Therefore, it's suitable for all the materials in our for the implant. And then the diagram you see is the example for the thermomechanical analysis for the material Teflon. Now the temperature of the test ranges from -150 to 800 degrees Celsius, and the sample dimensions has a maximum of 25 mm height to a 9.5 mm diameter, and the minimal change of dimension is 0.002 micrometer per degree Celsius to consider as a successful measurement. Now, my groupmate Ezra will explain the instrument for surface properties and mechanical properties characterization. Thank you.
Okay, and hi, Assalamualaikum. My name is Nurul Eza Hazira, and now I'll tell you more about the material characterization in terms of surface properties and the mechanical strength. So, for the first one, it is scanning electron microscope. The scanning electron microscope is used to quantify the grain size and distribution, and use backscatter electron detector, which is BSD, which inherently provide compositional information leading to fast and automated image analysis. And the elementary analysis using EDS. In this case, we are using EDS with SAM that can provide material information correlated to structure for ceramic materials and the best composition for desired mechanical properties and product performance. So, this is how it works. The first thing is electrons are generated at the top of the column by the electron source, accelerated and attracted by the positively charged anode, and it passes through a combination of lenses and apertures to produce a focus beam of electrons which hits the surface of the sample. The position of the electron beam is controlled by the scan coil, and there is two types of electromagnetic lenses are used, that condenser lenses and objective lenses. You can see in the diagram here that the first condenser lenses is placed there, and the second condenser lenses is placed there, and the other lens is the objective lens placed at the end of the stage. So the sample is mounted on a stage in the chamber area, and unless the microscope is designed to operate at low vacuum, both the column and chamber are evacuated by a combination of pumps. The level of vacuum will depend on the design of the microscope. So the position of the electron beam on the sample is controlled by a scan coils, which is placed above the objective lens, and these coils allow the beam to be scanned over the surface of the sample, which is in this case for the ceramic and polymer. So this beam is rastering or scanning, and as the name of the microscope suggests, and enables information about a defined area on the sample to be collected. As a result of the electron sample interaction, a number of signals are produced, and these signals are then detected by appropriate detector. So next, the 4-point flagellate test. We usually heard about the 2-point flagellate test and 3-point flagellate test, but this is 4-point flagellate test, which is specified test feature on a universal testing machine. The same application also used for 2-point and 3-point, also for the 4-point. The sample is placed on 2 supporting pins, a set distance apart, and 2 loading pins placed at an equal distance around the center. These 2 loadings are lowered from above at a constant rate until the sample failure. So that is, you place the specimen in between of the loading pins and the supporting pins, and we'll see how many force is needed to break the specimen. So this is the formula used. Okay, for the static compression test, we use this static compression test and the next test when the ceramic ball head is already being made. So in this case, we need to measure the maximum desired load that the ceramic ball head can reach, or when the head fractures. So basically, the how it works is you put a load, you increase the load on the ceramic ball head slowly, and little by little increase the load or the force, and you'll see what is the maximum desired load when the ceramic ball is fractured, and that's how it works. FDA approved testing, it uses the cyclic axial loading test. Same procedure with the static compression test, but using the cyclic axial loading, and there are certain criteria, which is the component fracture load must be greater than 46 kN, and none of the tested ceramic sample may fail at a load less than 20 kN in order for the ceramic ball head can be used. Okay, next, for the high density polyethylene that we are going to use for the polyliner, we use the tensile test to measure the force required to break a plastic sample, which exactly they stretches or elongates the specimen and produce stress strain diagrams to determine the tensile modulus. The tensile test for plastic provide the tensile strength, tensile modulus, tensile strain, elongation and percent elongation at yield, and elongation and percent elongation at break. So this is how the mechanical arrangement for the tensile test. And that's all from me. Thank you.
So, based on the explanation given by my groupmates and I, we have come to a conclusion. So we can come to a conclusion that to build a hip implant, we need to consider the ability of the device in terms of the mechanical strength and its effect to the user. The tests explained will be conducted to ensure the safety of the user for a long run. So we have agreed to come up with ceramic and polyethylene hip implant, as we believe the materials will be able to maximize the use of the device. That will be all from us. And lastly, here's other references that we used in order to conduct this research. Thank you.